Hello everyone, my name is Aarohi and welcome back to my channel. So guys, before we start, a quick reminder, please like, comment, share and subscribe. And now let's start today's lecture. So guys, in our last class, we learned how to prepare input for transformers. So first, we used a tokenizer to break the raw text into tokens. So you can see here, so this was our input sentence. My name is Aarohi and I love coding. And this is the first step which we performed on this raw input, raw text, and we got the tokens. And how we got this token? We used tokenizer for it. And the second job of tokenizer is to provide the unique ID to each token. So for my tokenizer provided this 101 as a unique ID. For name, it provided 223 as a unique ID. So like this, our tokenizer provided us unique ID for all the tokens. So this is the task which we performed on the input before giving it to the input embedding. Over here, we performed all these steps. And guys, if you are checking this video directly without checking the previous video, then I recommend you to check that video first, because this lecture is built upon that lecture. And guys, if you are not clear about the things which we have discussed in the last lecture, then it will be difficult for you to understand this lecture. So I recommend you to check that lecture. Link is given in description section also. And then we used this input embedding layer. So this became the input to the input embedding, and input embedding layer created embedding for all the tokens. So these are the different tokens which we have in the input. So for all these tokens, we got embedding vectors, right? And this kind of embedding vector we got for all the tokens. See, for my, we have this embedding vector. For name, the embedding vector is this. So this is the token embedding vector. For each token, we have one embedding vector. And the length of this embedding vector depends upon what I've told you in the last lecture. It depends upon D model, and D model simply means how many different values you are going to have in each embedding vector which you have for each token. So if the D model value is 512, that means each of these embedding vector will have 512 values. So this kind of output, these kind of embeddings we got from this input embedding layer. Now let's see the next step. And what is the next step? See over here. We are adding the positional encodings with these embedding vectors. Now let's understand why we are doing it. First, let's understand why, and then we will understand how we are performing it. So why we are adding this positional encoding with the embedding vector, with these embedding vectors? Because, okay guys, first of all, what these embedding means, why we created these embeddings. So we created these embeddings so that transformer can understand the meaning of each word, and transformer will understand the meaning of each token, each word, using these embedding vectors only. So that's why we prepared the embeddings, because we always prepare the input in the format which that particular model accepts. So transformer accepts input in the form of embedding vectors. So that's why we converted our tokens into embedding vectors. Now, over here, see, the task of transformer starts from here. And this part, this block over here is encoder. Okay. So from here, the inputs will go to the encoder. Why we are using this positional encoding? Let's understand. Now, from here, when the embedding vector of my, embedding vector of name, embedding vector of all the other tokens, my name, all these tokens, when the embedding vectors will go to the transformer, so at same time all these tokens will go to the transformer. See, if you have studied about recurrent neural networks, RNNs, so over there in RNNs what happens is input goes one by one. The word which is going first is at the first position, and the word which is going at the second position will be the second token, right? So over there, models understand that, okay, this is the first word, this is the second word, and this is the third word of the sentence or the sequence, right? But in transformers, all the embeddings, all the token embeddings go together, go at once to the transformer. So this my name is Aarohi and I love, all these tokens embeddings will go together at once to the transformer. So when all the token embedding will go at once to the transformer, what will happen? Transformer will not know which word or which token is at the first position or which token is at the second position, or what is the exact sequence of the tokens in the data set, right? And your transformer will not know whether the sequence is my name is or the sequence is my name. It will not understand anything. It will not know the position of the token. Transformer can only understand the meaning of the tokens using these token embeddings, but it will not understand the position of each token in the sequence. So, to tell the transformer that which token is at which position, we add positional encoding. If you'll add positional encoding, your transformer will understand, okay, my token is at the first position, and after my token, the name token is there, and the third token is, and the last token is coding, and the second last token is love. Okay, it will understand the position of each token. So to give the position of each token, we use positional encoding. Now, how we use positional encoding, what is the logic we follow, what is the maths behind it, all that part we will cover now. So, for that, let's open the paper of transformer. So, this is the architecture of original transformer, the first transformer which was introduced in 2017. Now we are opening that paper. Attention is all you need. This is the paper name. So we will open that paper and we will see what is there in that paper related to positional encoding. So this is the paper. Here, this is the transformer architecture which I've shown you. And now just scroll down and we will go to the section where they have discussed about positional encodings. See, this is the section. They are discussing about positional encoding over here, and you will see that they have used this formula, right? We have this formula in the form of pair, means one formula is using sine function, another formula is using cos function. And why we are using this sine and cos, what is this position over here means, what is this I, what is this D model, let's try to understand all this. So using this formula, they have added the position of each token with the token embeddings. Now let's try to understand this part. So guys, we are going to use the same input sentence which we used in our last class. So this was our input. These are the two steps which we got after tokenization. Then we got input embeddings, and these are the input embeddings. After that, see, in this formula, you will see POS. What is this POS? First, what is this PE? PE means positional encoding, and we want to find the positional encoding. And this POS means the position of token. Okay. And first, let's understand this position part, POS. What is it? And then we will understand the entire formula. So, for that, just see here. So, in our input sentence, this is our input sentence. So the first token is my. Our first token is my, and the position of that token is 0. Index always starts from 0. So the position of my is 0. POS is 0. Okay. This POS for my token is 0. Then we have second token, which is name. And the position of name token is 1. So when the token is name, at that time this POS will be 1. Okay. In the same way, for third token, our third token is for is, what is POS? POS is 2. In the same way, for Aarohi, it is 3 and I love coding. So in the same way, for and we have 4, for I we have 5 position, love have 6 position, and coding have 7 position. And now what is this I over here? Let's understand this I part. So guys, for this, suppose our D model is 4. So guys, for simplicity, I'm writing 4. And I have told you D model simply means how many values you are going to have in each embedding vector. In the same way, D model will also be used in positional encodings also. Okay. So over here also, in positional encoding also, the meaning of the purpose of D model is same. Means how many floating point values you're going to have in each positional encoding vector will depend upon the D model. And if the D model is 4 for your token embedding vector, then D model for your positional encoding vector will also be 4. We need the same numbers in embedding vector, token embedding vector, and in positional encoding vector. Why? That purpose I will tell you in some time. For now, just assume that D model is 4. That means we are going to have 4 values in each positional encoding vector. And we know that the total number of tokens, how many tokens we have in our input sentence? We have 8 tokens. Let's go above and see how many tokens we have. We have 8 tokens, right? 1, 2, 3, 4, 5, 6, 7, 8. We have total 8 tokens and the D model is 4. And for example, assume we know that the first token is my. So I'm showing you the example with the help of this first token, my. Okay. So assume for my, the token embedding is this 0 0.4, 0 0.5, 0 0.6 and 0 0.7. We have these 4 values. Why these 4 values? Because the D model is 4, and if the D model is 4, that means you're going to have 4 floating point values. And for the simplicity purpose, I have written the values like this. So this is the, what is this? This is the token embedding. This is the token embedding. And from where we got these kind of input embedding vectors? We got these kind of input embedding vectors from this input embedding layer, right? For my, we have this vector, embedding vector. For name, we have this embedding vector. So I'm showing you the example right now. With this, I will show you how we are going to add position with my token. Okay, in the same way, you will add positions of those tokens, okay, similarly. So this is the token embedding. And guys, how we got these values? Remember, I have told you in the previous class that initially these values are random, and with training, these values are learned. These are learnable parameters. So this is the token embedding. And now let's talk about the positional encoding. Now we are talking about the positional encoding vector for my token. Now we want to create the positional encoding vector for this my token. So for that, you will also have 4 values. So let's say initially the values are 0 0.0, 0 0.1, 0 0.2 and 0 0.3. So we are also having these 4 values. How we are getting these values, that part we will discuss in some time. But right now, just understand the number of values in the token embedding vector and the number of values in the positional encoding vector will be same. Both will see what is the D model, and whatever the number is written in D model, those many values you will get in embedding token embedding vector and in positional encoding vector. Now, why we need the same number of values in both the vectors, positional encoding vector and the token embedding vector? Because we want to perform the element wise addition on it. Using that element wise addition, we will add the position of each token with its embedding, okay, token embedding. So that means the first value of this token embedding vector will be added to the first value of this position encoding vector. This is what element wise addition means. And the second value of this vector will be added to the second value of this, and the third value of this vector will be added to this, and the fourth value of this vector will be added to the fourth value of this vector. And this is how, when you will perform the addition, and the final embedding which you will get over here will have the token meaning, the meaning of the token, and the position of that token. Okay, so let's fill the values here. So we will get 0.4 over here, and here we will get 0.6. You will, when you will add this to this, and then we will add 0.6 and 0.2, so you will get 0.8, and then you will add 0.7 and 0.3, you will get 1.0. So this is the final vector where we have the position information and the tokens meaning information. Both the things are here, and this will become the input to the encoder. So this is the basic idea. We will understand the formula right now, but just for now, just this is the overall idea, that this is how you will get the positional encoding vector. And this thing will happen for all the tokens. Right now I have shown you how to do it for the first token, the my token. For the name token also you will perform the same thing. For all the tokens you will do the same thing. And guys, one more thing, this positional encoding vector, for each token you will get this vector in the starting, and throughout the entire training this vector will remain same. The values of this vector will not change. Means if this is the positional encoding vector for my token, you have created it once, and then throughout the entire training process this positional encoding vector will remain same. It will not get trained. Like earlier in our last class we have seen that for each token we have a token embedding vector, and these values are random initially, and with training these values are learned, these values keep on changing, and slowly these values will start making sense, right? But positional encoding vector is totally different from this token embedding vector, because here we are not changing the values of positional encoding vector. It will remain same in the entire training process. Now next question is why these values are fixed and why these values are not changing, right? These positional encoding vectors, they tell the position of token, right? So in our case, our example is my name is Aarohi and I love coding. So over there, the position of my is fixed. The position of my will always be position 1. So the positional encoding vector tells the model about the position of a token, and it never changes because the word order is fixed. So that's why we create these vectors once and we don't change it later. But over here in token embeddings we are training the model to understand the meanings of the token. So that's why these values keep on changing, because model is learning them, and based on the learning these values keep on changing. But in positional encoding vector, so the position of the tokens are fixed, so you just need to tell the model the position of a token once only. So there is no need to change those values because the position of the words are fixed. So that's why these values are fixed. For all the tokens you're going to have a positional encoding vector, and the value will be assigned once in the starting, and throughout the entire task that vector, positional encoding vector for that particular token will remain the same. And now guys, we were discussing about this I, right? So now let's understand what this I is, because you have the idea of the things which you need to know before understanding this I. So I is index. Now let's understand what this I means. Okay. So in positional encodings, so this is the positional encoding vector for my token, right? So this vector, what this vector tells to the transformer? This vector tells the position of the my token. So I simply means the index of the numbers inside the positional encoding vector. So this 0.0 is at the 0th index, and this 0.1 is the is at index number 1, this 0.2 is at index number 2, this 0.3 is at index number 3. So this I simply means the index of values inside the positional encoding vector. Now you know what is I. Let's see this formula. Now you know what is this I, what is this position, right? POS simply means 0, 1, 2. My token is at 0 position, name is at 1 position, is at 2 position. And I simply means the positional encoding vector which you are going to have for each token, right? The positional encoding vector for each token. Over there, inside that positional embedding vector, the values which we are going to have, this I represent the index of those values. Now we have two formulas over here, sine and cos. Now let's try to understand this. Whenever you want to create this positional encoding vector for each token, at that time, what you're going to do, see, you will work in a pair. Okay, so how this positional encoding function works? So in the paper they have added one rule that you will not give this value. We know this is the first value is at the 0th index of the positional encoding vector. We know this value is at the first index of the positional encoding vector, and this is at the second index, and this is at the fourth index, right? But you will not give single value. Okay, you will not work on single value at one time. You will work on two indexes. You will work in a pair. What that means, now let me explain you that. So let's write this positional embedding vector over here, okay, to make you understand. So the first value is 0.0, second value is 0.1, and then we have 0.2, and then we have 0.3. So these are the positional encoding vector we want to create for my token, okay, to tell the position of the my token. So these are the four values. So the value, this and this value, the first two indexes, one pair, and then these two values this is the first pair and this is the second pair. So like this, you will work in pair. Why work in pair? Because we have two formulas over here. One index will use this formula, second index will use this formula. Okay, what I'm saying is, first index will use the formula, the sine formula, and the second index will use the cos formula. That means the even indexes will use the sine formula and the odd indexes will use the cos formula. And that is why there are two formulas in the original paper, in the positional encoding section of the original paper, because they added a rule that you will work on pair of indexes, and the index, the very first index is 0, which is an even number. Always a even index will use this sine formula and the odd index will use the cos formula. Now, why we are using these two formulas over here, sine and cos? So guys, we want to add the positions, and basically over here they are trying to create a wave. What is wave? So this is how wave look like, right? So one, we are going to create two waves. One is a sine wave. Sine waves always start from 0 position like this, and cos wave starts from here, from 1 position, right? Like this. So we are going to have waves like this. So guys, ignore my drawing. Okay, just try to understand the concept. So sine wave starts from 0th position, 0 position, and the cos wave, the value of cos will be 1. Okay, because this is cos is always a little bit shifted to left. Okay, so when the value of sine will be 0 and the value of cos will be 1. So this is the difference, right? When sine is at 0, the value is 0. When sine at the cos at 0 is cos at 0 is 1, right? So the combination of these two waves will create a wave. Okay, and that wave tells the position of the token. So guys, this is how we get position signals. Okay, so see, now you know what is position. When you are going to work on my token, at that time the position will be 0 to I, you know what is I simply means the this I simply means the index of the position encoding vector, the values which are there inside the position encoding vector. And then for my token you will write position 0 over here. Suppose you're working on my token, so at that time, over here, what would be the value? Position will be 0. So remember, I've told you that for my token, position will be 0. So for my token, we have 0 over here. And then we have this 2i. I, you know, I is the index value of each number which is there in the positional encoding vector. And d model, for example, for simplicity purpose, let's say the d model is 4. So you will have a 4. So you will solve it in the same way. You will fill values in it. You will solve it. So let's solve it for first 2 or 3 tokens using this formula so that you'll get an idea how we are getting the positional encoding vectors. I have already written this part so that it will be easy to understand in a clear way. So we are talking about the first token, which is my, and the position of the position of my is 0, and dimension 0, 1, 2, 3. What does this mean? 0, 1, 2, 3. 0 means simply means the 0th index of positional encoding vector which we are going to create for my position my token. Okay, and the 1 means simply this is what it means. So this is the 0th dimension, this is the first dimension, this is the second dimension, and this is the third dimension. So this is the index. This dimension simply means the index. And the formula, if you'll apply this formula, so the position of my token is 0, so that's why 0 over here we have 0, and then divided by 1, you'll solve it, you'll get 1. Okay, and the value you get is this. So this is the first value of your positional encoding vector which you get for my token. Okay, and then we are using the cos formula. So I've told you that we are going to use it in a pair. So these two dimensions are one pair, these two dimensions are one pair. So for even index, you are going to use sine formula. For odd index, you going to use cos formula. In the same way, sine formula here and the cos formula over here. So you will apply these formulas. Position you know is 0, and we are working on this token. And these dimensions you already know that 0 index, first index, second index, and third index. Okay, so you're going to solve this formula and you're going to have these 4 values, so this is the positional encoding we got, positional encoding vector we got for my token. In the same way, you will get the positional encoding vector for next token. And what is the next token? Next token is name. What that means? That means that under dimension you will have 0. Okay, let's do like this, that under dimension you're going to have 4 values, 0, 1, 2, 3, right? This is the dimension. Then we will use the formula over here, right? And then we will get the values over here. And this time you will use sine. What is the position this time? Earlier the position was 0, that's why we have written 0 over here. This time the position is 1. The position of which token? We are talking about name token right now. So we have solved for my, and now we want to get the positional encoding vector for name token. So for name is at which position? See, name is at position 1. So over here we will use 1 now. Over here also we will use 1 now. Rest of the values are the same. See, sine 1 divided by 1. In the same way, you will apply other formulas and you will get the positional encoding vector for name token also. Okay, you will get 4 values because the D model is 4. So in the same way, guys, you will perform the same the method for all the tokens. And I have told you, once you get the positional encoding vectors like this for all the tokens, what we are going to do, I have shown you the process over here, that you will add the token embedding of that token with the positional encoding vector of that token, and you will perform element wise addition. Means this will added with this will get added with this, and this will be added to this, and this will be added to this. And after that you will get a final vector which will have the information about the token meaning, and which will have the information about the position of that token. And now your input is ready, and now you can give that input to the transformer. And in my next lecture we will see how transformer will work on it, how transformer will learn the things. But guys, please like, comment, share, and subscribe, and I will upload the video as soon as possible. Thank you so much for watching.